Hello everyone and welcome to the new episode of CPP Next. During this episode we will explore re-entrapped cast, how to use it correctly and how not to misuse it. Re-entrap cast is a super important feature in C++ that can get misused a lot. And when you misuse it and you don't understand exactly how it's supposed to work, you will get horrible undefined behavior in your code. When you get this undefined behavior, it means that you will spend a lot of time debugging your code without actually understanding where this crazy thing comes from. And I just want to save you guys from that. So during this episode, I will explain in simple words what does it mean to use re-entrap cast, how to use it correctly, and how not to misuse it. How not to use it for those things that we told that it's okay to use it for, but they will just create the UB for you. So let's start. In very simple words, re-entrap cast can translate one type to another, but if and only if those types are interchangeable, or in other words, it means that those types can be looked at as the same type. That means if a type is not exactly the same as the type you're trying to convert to, you will get undefined behavior. To explain that, we will start with an example. In this example, we will have four classes. As you can see, those four classes are pretty simple. We just have A that has an integer in it as a member, B has the same named member and a member function. Struct C is inheriting from A, struct D has multi-inheritance, and it inherits from A and from B. So let's say we have an instance of class B. And let's say we want to translate it into A. For now, everything seems to be fine. But if we will try to access the data member inside the class, this is undefined behavior. We cannot access a data member from the class because B is not A. They are not subclasses, they are not the same, and that means that the compiler doesn't know exactly what you're supposed to do with this pointer. And so this is undefined behavior. Now let's change it just a bit. Instead of B, we have C. We want to translate C into A, exactly the same as we wanted from B. But in this case, this is absolutely fine. Why is it okay to do that? C inherits from A. That means it's a subtype of A, and that means it is an A. That means that it's the same type, and reinterpret cast actually works fine. This is one of the use cases when using reentrap cast is fine, and it is great to do that if you need to actually downcast into your inherited class. It's much faster than dynamic cast, and it works here. Now, what will happen if we will try to do the same for D? And we will spice it up a bit and use B instead of A, and we will try to call the function. It will seem that it's fine because D is actually a type that is inherited from B, and it should be fine to call a function because it's the same type. But no, and you can actually see it here from the compiler itself. It's already telling you that you have a problem and you shouldn't use that. Why is that? Because this type doesn't have standard layout, and because it doesn't have standard layout, reentrap cast doesn't work, and you will have an undefined behavior. So please note those small things, those small changes, and try not to do that. Listen to your compiler. It's already trying to tell you what you're doing incorrectly, and it's trying to tell you how you should actually derive what you want and get the type that you actually want from it. Now, let's talk about one of the most common mistakes done with reinterpret cast. Let's say that we have a floating point f. and we want to translate it into an unsigned integer. Although everything seems to be fine, this is an undefined behavior. That happens because floats and integrals are not the same type, and you cannot do the conversion between them. So how can we do it correctly with reinterpret cast? There is one exception with reinterpret cast for chars and bytes. Everything, any type can be translated into a byte or char, and then all the chars and bytes can be translated back into an actual type that you want. So in this case, we need to do something like that. And in this case, this is not undefined behavior anymore, because we have translated the floating point into a char pointer, and then we translated the char pointer back into an unsigned 32-byte pointer. Still, it has its own problems. Stay tuned for other episodes when I will explain exactly the problems when using reentry cast like that. What should you do? And the answer is use bitcast that was introduced in C++20. This is absolutely safe and defined behavior. We have a lifetime for I, and everything actually works fine. Preferably, you should always use bitcast for primitive types. But bitcast has a problem. The types have to have the same size. If you have different types with different sizes, bitcast will just not work. If you want to translate types with different sizes, you will have to use one of the libraries that are written, and I will introduce it in the next episode. That library extends bitcast to do it on any type of any size, but more on that in the next episode. Things get even weirder when you try to work with booleans. In this example, we will explore two compilers. We will see how Clang reacts to a reentrip cast to bool, and how GCC reacts to the same thing. So let's start. You would think that B will be true because the byte is not 0, but it's false. If you will make a slight change and change it to F5, B is true. So what's going on here? Let's look at the binary layout of the number x. As you can see, for F6, the last bit, the least significant bit, is 0, and it's false. If we change it to F5, the least significant bit is 1, and then it's true. So Clang is taking the least significant bit and sets it to be the value of the Boolean. A little bit weird, don't you think? Now let's look at the same program and what GCC does with it. So you can already see that GCC's answer is a little bit less surprising, and you get true with F6. If we use F5, we still get true. So what's going on here? Let's do it a little bit different. Let's add 2 zeros or 1 byte of zeros in the end. And voila! What GCC does is basically taking the last byte of the number, and if it's 0, then the answer will be false. If it's not 0, the answer is true. Still, it's not exactly what you wanted, but GCC does something a little bit less surprising. And again, you should not use it. It's just undefined behavior. It's really, really bad, and you should avoid it as much as you can. In conclusion, we have to understand what reinterpret cast does. We can cast to bytes and from bytes. We can cast into the same type. If we have inherited from a different type, we can cast to that. We can save precious milliseconds when doing that instead of dynamic cast, but everything else might be with an undefined behavior. So use reentrap cast wisely. If you can't, use bitcast. And in the next episode, I will show the extension library for bitcast. Stay safe and use safe C++. See you in the next episodes.